understand them. If you want to come there and talk to them, well, it's good. People can listen to what you have to say and form their own opinions. So Murli did his PhD, he did his undergraduate work in Goa, and then he did his PhD in IIT Madras, and after that he done various things, but he went to the US to do a postdoc with Lowell and Harper at the University of Illinois Champaign. He came back to India, he was here for some time, and went back again to do some research, and now he's back. So we're happy that he's here and look forward to hearing about it.
Thank you so much. Good afternoon. I thank Dr. Raghavan for giving me this opportunity to speak here. Without much ado, I'll directly get into it. So this is something made by my student Vivian, so I thought I should put it up. So the talk would be titled, "Why do we need oxygen?" I claim, I boast that this is one of the most important findings ever, and I'm here to present and define my works. So I have got a very radical answer, pun intended. Currently I am working through my own trust, basically means I am unemployed. So the contents would be basically on three parts. First, I would talk about the story of murburn concept. Murburn concept is a term that I coined, which is going to be the explanatory paradigm for oxygen utilization. Then the crux of the talk would be about the chemiosmosis theory, or the EPCR, Electron Transport Chain, proton pumps, chemiosmosis, Rotary ATP Synthesis. That is the overall paradigm that is available for cellular respiration. Then the cellular respiration is also called mitochondrial oxidative phosphorylation, that is abbreviated thus. So how does my murburn concept explain that? Then the outcome and the impact. So before I tell you the story of murburn concept, I'll tell you briefly about my background, because it says about how I approach problems. The murburn concept is my story, basically. That's what I am. So I did my BSc in zoology. Basically, I was smitten by life. I like life forms. So when I was at graduate level, I thought I knew a lot of biology. I was studying biology. All teachers were very happy with me. So I did biology, right? And then it so happened that K.R. Narayanan, the president, he was the science and technology minister at that time. And in my small time college in Kerala, he got the national level exhibition on science and technology. So there I came to know about biotechnology. I wrote the entrance exam and got into MSc. I gave Bioenergetics as my choice. Obvious reason, Goa, cool place. And I also liked Jacques Cousteau's Secrets of the Sea and all that. So I thought I'd be doing underwater diving and all that. Guess what? It changed out to be something totally different. Biochemistry, biotechnology was something very different. So in my master's first semester, I was writing the biochemistry exam. I cried, tore my answer sheet into two, ran away. That was my bigger happening in my master's program. So the teacher asked me, why did you do that? You were getting even then the topper. I was a topper in college, but when I came to master's level, I suddenly realized that I didn't know much. That was a realization, you know. And then I did my whatever and master's, got through it. PhD, I did it IIT Madras on lipases. All were generally, I stuck to enzymes, proteins, because genes I found it very difficult to relate to. I like this starry kind of, everybody likes actors, nobody cares much for the directors, they were behind the scenes. And I was also a very normal kind of a person. Proteins interact with everything out there. DNA interacts only with proteins. So let me take proteins. So that was the reason why I took. So basically I stuck to proteins. For me, the big happening in PhD was one of my friends died. So after that I started wearing only white and black. I made a promise to myself that I have to do something to get his death certificate from the authorities. I had to go pillar to post. So I thought I'd change the world. I'll come back, make this place a greater place and all that. So, but before that I had to do some good science. So I went to US after doing my postdoc work in CNRS for a brief stint on epoxide hydrolase. My world was all this thing that you see: collision theory, transition state theory, the lock and key theories and induced fit and all that. So until then, my life changed big time it changed in Urbana-Champaign, University of Illinois Urbana-Champaign. Lowell Hager, he is the hero of my life. National Academy of Sciences member, 25 years chair of the department. Okay, so he was a very big-hearted guy. I had 3 labs for myself, all the time for myself. I was married, I had my kid. After 1 year, I said to my wife, please go back. You know, Indians, we can afford to do that. Wife doesn't leave you. So I said, please go back. So I had the 1 year full to myself. First year, he introduced me to the heme protein. That became my love of my life. Basically, he was the person who had discovered the enzyme chloroperoxidase. It's a fungal enzyme. You see, it's soluble, highly hydrophilic. It has got a hydrophilic pocket. It's a heme thyroid enzyme, just like cytochrome P450. It's another enzyme that I'm going to talk about now. So I'm just bringing these 2 protagonists here. Cytochrome P450 is the enzyme that metabolizes majority of the xenobiotics that enter our body. And chloroperoxidase is responsible for 90 to 95% of the chlorinated molecules that we find in nature. So as of today, these 2 enzyme mechanisms are mine. Mine is a standing mechanism. Murburn concept. Both are Murburn concept. So the area I chose, I came only because of Lowell Hager. And before I start my work, all my work is always, I pay tribute to Lowell. Okay? He is the person who made me who I am. In his lab, I started loving science for what it is. So this enzyme is very different from whatever I had studied before. All the enzymes that I had studied before, they used water to break molecules, they were hydrolases. This was very different. It was making water, and most importantly, all those induced fit, lock and key somehow were not very clear in this kind of mechanism. And it was one of the most versatile enzymes that you could see. The kind of substrate diversities that it showed, single electron, 2 electron, the gamut of reactions that it could catalyze, unbelievable. So in 1999, what it did, so for about 7 years I had worked and I had got 2 papers. In 7 months I had got 3 papers in the first year of my postdoc there. So this paper I asked Lowell to retract. It's a National Academy of Science paper. It's got 79 citations. It's junk, I believe. This is an okay kind of work. This is a stunt. So why I am putting it there, it's all for a reason. Because I slowly outgrew this kind of stunts of publishing paper. In the second year, Lowell had given me a lot of projects. I said to Lowell, this is my last year in research. I want to go and do social work. Give me this year. I'll do whatever you ask me to do, but let me also do certain things on my own interest. So he said, feel free. So that's when I started. I was given certain projects on Ecopetrol, a company. They were trying to demetalize crude petroleum. And my boss had a multi-million-dollar project of making ternary solutions with the enzyme and all that. So I said, why do you have to do it in such a roundabout way? Take salt, take bleach, take acid, mix it up, you get the same reaction. So what happened is his multi-million dollar project got screwed, but the point is that he didn't really care. He was bothered that this person is really trying to solve problems. And US Navy project he gave me, I said it's a poorly framed project. He accepted it. Directed evolution, same, I found certain ways. He was happy with that. The point is, These are the important papers. Here, it was a simple BBA paper. Until then, they thought that peroxide inhibits the chloroperoxidase at a particular point. I said, actually it is peroxide getting depleted. There is no peroxide in the reaction. That is why the exam doesn't work. This was just a stunt. It got published in a much better journal. So then I tried to get Lowell to think out of the active site for explaining the mechanism. It took me about a decade to convince him to give his name. So this was a paper that we published in which we showed the one electron reactions and the two electron reactions work very differently. So Janus is a Greek god with two faces. So the enzyme works in two different mechanisms. Don't worry about the text. Many of my slides will have too much text. Look at me, I am the beautiful guy here. Don't go too much with the text, please. Thank you. I just put it out there so that you can see all the arguments. I sent this, so that you could see the arguments out there. So in this, I showed very clearly the enzyme works using I couldn't get Lowell to put his name completely outside the enzyme, somewhere out, preferably on the surface or something he could give. In 2006, this paper was a two electron reaction. It's a chlorine atom insertion reaction. This reaction was supposed to be active site reaction. I showed that this is also outside the active site. But this I deferred. This was Lowell's standing mechanism and I deferred with him, and I had a tough time trying to publish it. If I had put his name, it would have been easier for me, but I got a little bit too carried away. So it took me 6-7 years to publish it on my own. Here I showed that selective, that is, if you give 5 different substrates, the enzyme reaction can choose out of A, B, C, D, E, it can choose C. And specific, if there is ortho, para, meta, 1, 2, 3, 4, 5 position on a substrate, it can attack only one. When it does not occur in the active site. Please understand that. These are active site associated, attributed facets. I showed that this is not like that. So these are very important aspects that went on to build the murburn concept. So I didn't tell you one part. In 2000 I returned. 2001 I had come back from US, started doing my social work, and I thought in my countryside local people will like me and slowly I'll become the Prime Minister of India. It didn't happen, right? I became a pauper. I had to go back to US, and 2004 I go back, start working in a Raman spectroscopy lab, and I deferred with the PI there. PI happily says that you have to give it like this, you have to say this is the way. I said, no, the data is here, you take the data. He threw me out. So I moved on to another lab on which they made me work on cytochrome P450s. Same, I did not change my area, heme proteins. I stuck with heme proteins. So there I was given an NIH project in which I had to minimize these I had to find the strategies to minimize reactive oxygen species. Reactive oxygen species were found to be produced when drugs were metabolized. So in the pipeline where they optimize a drug lead, the reactive oxygen species had to be minimized. So I report in 6 months to my PI, sir, your project is framed wrong. We have to change the project. This project is framed wrong. Without reactive oxygen species, this enzyme won't work. He says, bye, you out. I go to another lab. Did change the area. Stuck on with cytochrome P450s. That guy threw me out in 3 months. For the same thing. Okay, I said land of opportunities. Here I go. I come back to India, 2006, but before I left US, I made sure that I put it in our site. Okay? And he had it retracted. He promptly wrote, this guy doesn't belong in it. If you go, you can see that he has withdrawn it. But Cornell University has good policies, they retained it. But here I showed, first time I argued that diffusible reactive oxygen species are mandatory in routine oxidative metabolism. It took me very long time, 10 years, one of my PhD students is sitting here, 3 PhD students, so many masters and BTech students, they had to graduate. I had to put so many kuti papers through BBRC, all that, you know, in heme enzymes. I put some papers. This paper is very important, if you see. I have shown cyanide does more to inhibit enzymes than merely serving as an active site ligand. Azide, I showed that azide can activate heme enzyme. Now if you see, cyanide and azide are traditional binders and inhibitors of heme enzymes, if you know heme enzymes even a little bit. So I showed that, and then some other stories. And 2016, this was all halwa, everything together, all my students together. But it's a very, very important progression. I am just trying to show how I made my story, okay? So that was the heme story. Heme is like, you know, the chloroperoxidase is like cocoa. You play cocoa, nobody cares. You play soccer, people note you, right? Cytochrome P50 is a drug metabolizing enzyme. Chloroperoxidase is a fungal enzyme. Who cares? So that's what. So, but then cytochrome P50 is a very vicious field. Nobody would like you to change their concepts. So, but then that place I slowly and surely published, explained how different enzymes show substrate inhibition. How can you explain? How can you explain super inhibitions in cytochrome P50? I showed in this system heme was supposed to activate oxygen. I said the reductase enzyme is in fact activating oxygen. That's this paper. Then the transmembrane segment was supposed to play a role in bringing these proteins together and affinity mating and all that. I said even without those transmembrane segments, they were quite happy. So basically, systematically, bit by bit, I broke the backbone of the established paradigm. And the most important one was here. The last one, it was in 2016, it was the BUCD paper, which Danny was also a corresponding author. Here, I showed that the electron transfer, which was supposed to occur through protein-protein complexation, long distance outer sphere electron tunneling and all that, I took those two proteins, separated them by a dialysis membrane, voila, the electron transfer still occurs. And that experiment I did when on the day I was fired, the last day of my work at University of Arkansas at Medical Sciences. I'm very proud of these things. I was fired, but I kept my poise, balance. I knew what I was doing. Now, in 2016, this paper, I could finally put my foot into the door, wedge into that, how to put a comprehensive explanation in. They'll allow you to say the elephant's tail is like a brush, they'll allow you to say it's like a pillar, all that. They'll never allow you to put the whole picture there. So, I went to US last time, 2015, last part. Lowell had passed away. I applied for a visa to attend his commemorative function. As usual, we Indians, we have great privilege. The visa came after the function got over. But I used that to go to US, stayed there for 6 months, okay, and attended 3 conferences. In those 3 conferences, all these people, they would come, they'd see my work, they'd do that, and they'd walk. All these so-called big names. They would not do anything, they will not say anything negative, nothing positive. There was one guy in the Gordon Research Conference, Gabriel Kuruchian, he's a very big name, he has got his own company and all that. He was giving a talk and I said, don't you think what you say doesn't make any sense? I mean, I said something to that effect. And he said, very true. He was very honest, he appreciated. I don't think these molecules should go in. All these simulations that I do, it is to please people. He said very openly. And then he helped me get this paper in. So I had all the experimental data, but I could not publish it. I had to put a hypothesis paper in silico pharmacology. This is a small time Springer journal. So I put a hypothesis paper, put the foot in the door, and then the next puppy came in easily. Just when I said all that I had saved, 20 lakhs was done, you know, I was practically a pauper, on the verge of giving up. So you can see murburn concept explains. Here I have put 50 arguments why the currently prevailing explanation doesn't do a thing, why this explanation explains it. So this is the murburn concept. So I'm talking about xenobiotic metabolism here. It is not about oxidative phosphorylation yet. I'm going to come to it later. So the current hypothesis the prevailing hypothesis on the xenobiotic metabolism was the substrate, diverse types of xenobiotics come and bind to the heme enzyme that changes the spin state, changes the redox potential, reductase binds, then it receives electrons, oxygen binds, then so many steps, reactive oxygen species get released, all that, voila, it goes through these steps. So it's a multi-molecular sequential scheme, alright? So what I say, this is all nonsense. The oxygen is activated by the reductase directly, reactive oxygen species are formed, they are stabilized by cytochrome P450, and they have very transient binding with the substrate, if at all. That's all. So this is the difference between the erstwhile concept and the murburn concept. So you see how it changes. The Fisher's lock and key, the Koshland's induced fit, Ehring's transition state, all that Michaelis-Menten, all those fundamentals of enzymology, very different from murburn concept. Here you see the erstwhile hypothesis, substrate binds, it has to move in, and then all the atoms have to be in bondable distance, and then the substrate after hydroxylation goes out. In my hypothesis, the substrate of diverse types can bind to diverse locales on the enzyme, and it can get the reactive oxygen species stabilized here. It can react in and around the vicinity of the enzyme. There's a lot of uncertainty involved. So the kinetics that you see is not Michaelis-Menten. The Km, the Ki, they are all very different. So it's a paradigm shift in enzyme chemistry. So this is what happened. Now what does it do in terms of explaining things? It's explaining substrate diversities of how we have one cytochrome P50, for example. These are the different drugs that are metabolized by one cytochrome P52C9. How can you explain such diverse topography being metabolized by one single enzyme? If you see that erstwhile hypothesis, all have to stick to the active site, they have to go on through that active site, full cycle, all that. It doesn't explain anything. So, then explains why.
Induced fit should explain this. Right?
Pardon?
Induced fit, like.
Yeah, induced fit could explain, but then how can all this different? They have all different types of.
No, it has to have just one benzene to initially latch on, and with a few hydrogen bond acceptors and donors.
Well, that can be an explanation. But then, if you apply Occam's razor, you can have this just one CYP. If you see all CYPs have diverse substrates. Then we will have to say that all these CYPs have all some fundamental recognition features. But then there are no such fundamental features. That is what. So by application of Occam's razors, mine is a preferable explanation. So then there is another aspect. There is only one reductase. There are hundreds of cytochrome P450s. How can this single reductase, which is found at much lower ratio?
No, but phenobarbital.
It is induced. Yeah, phenobarbital
induces
correct.
cytochrome.
Correct.
Okay, P450.
Correct, Dr.
So your
Surya. Very correct. Phenobarbital does induce certain, but all these don't. So the majority do. Some do. Definitely some do. Correct. Thank you. So then there are certain other things that the majority of the picture is what I'm talking about. So then kinetic isotope effects and secondary oxidations, which have more mechanistic significance, that are explained. Then most importantly, this explains hormesis. Hormesis is a very interesting phenomenon. Hormesis is when you put a drug at say micromolar level, you don't find any effect. You put at nanomolar level, you find effect. Contemporary physiology cannot explain that because receptor based binding, it should go up with the increase in concentration. But my reaction has radical based effects. Radicals are more stabilized at lower concentration. So formation can give that. So atypical kinetics, all that can be explained. So this brings about a big change. So now that I have almost taken 25 minutes, now let us come to the crux. So I have shown you the credibility factor with which I come to you. I have explained the mechanism of two heme enzymes. One was a simple heme enzyme system which used peroxide and heme enzyme. The other one was NADPH, oxygen, flavoenzyme and heme enzyme and the substrate. This murburn concept for application for mitochondrial oxidative phosphorylation, this is a totally different ballgame. It's a very complex system. How many of you want a, let's not spend too much time on the videos. I'll just give you a crash talk on this. I had gotten some videos, I'd rather not play it. So, most of you are research scholars. Let me just give you a brief overview. So, you know that there are two Nobel laureates in this area, right? Peter Mitchell and Paul Boyer. Peter Mitchell for chemiosmotic theory and Paul Boyer for Rotary ATP synthesis. Now, basically, it has got four components, this current explanation. One is an electron transport chain. 1, 2, 3, 4 major protein complexes. Complex 1, complex 2, complex 3, complex 4. These two are heme and these have iron sulfur and heme and mixture of iron sulfur, heme and flavoproteins. These two are flavoproteins only, they don't have flavors. Just have iron sulfur and heme as cofactors. Now, this puppy is a totally different enzyme. Works totally independent. Complex 5, ATPase, F0, F1, ATPase. Okay? Not F0, FO, F1. Sorry. So the current hypothesis is NADH gives electrons, goes like this. It goes to CoQ, coenzyme Q or ubiquinone, and then goes to complex 3. From complex 3, cytochrome C takes it and then gives it to complex 4. All the while, oxygen is happily, dedicatedly sitting there at complex 4, waiting for its share of 4 electrons, 4 protons to become 2 molecules of water. So, this is the electron transport chain. There is the second component, which is the proton pump. Proton pump, as the electrons pass through it, protons are pumped out through this. These 3 proteins pump protons out. 4 protons per each protein complex. So 12 protons go out through one battery. That's the mechanism. So the electron transport proton pump component over, then the protons come out and they come back through the ATPase. And then this thing goes round and round when the protons come in and they make ATP. This is the current hypothesis. All of them are wonderful equations, all balanced to give all that. You know, so many protons are used up in each cycle. Wonderful. Now, you see that ATP synthesis has nothing to do with oxygen at all, other than oxygen serving as a terminal electron acceptor. Only protons are needed for ATP synthesis. Okay? Now, what does this model look like? This model looks like some kind of system in which you have, this is a simple model, let's say. It's like a dam. You have water flows in, this turbine goes round and round. You generate power and that's it. Only one difference, the water has to get pumped back. Okay, that's the model. Protons get pumped back. That's the model. It's a fundamental difference, but it's a very big difference. So in terms of modularity, you can compare it with a car. See, basically, fuel is burnt in the engine. That is translated to that back and forth motion is translated to a circular motion. That circular motion is tapped by the alternator to recharge the battery, and the chemiosmotic principle can regulate it. This is the kind of modularity that the current hypothesis seeks. Now sadly, this modularity, all that it seeks, all that is lacking. Now, why do I challenge this hypothesis? Please understand, this is very important. Every living system that uses oxygen, everything uses this. Fundamental logic of life. So, fundamentally, why I did not like it. When I was a master's student, when I had to study this, I hated this. I could never accept why it looks all so crazily deterministic. You know, there is no chemical logic involved. Though I am a biologist, I don't like to see all these having, you know, this Harry Potter-like magical powers, you know, mitochondria. They are all simple chemical systems. They cannot have too much of deterministic logic. Already all elements sitting there. How can you have a gambit logic? Protons go out and when they come back they synthesize. How can evolution get that kind of a thing at the very outset? Because energy tapping logic has to form at the very outset. How can that kind of a gambit logic be starting at the outset? Then all this soluble cytochrome C, coenzyme Q, they are so dedicated, they take that electron from one place, all of them go. Why? And you know, it's unbelievable the way the low efficiency scheme is incorporated. If you see if you have studied glycolysis and all that, you would have seen substrate level phosphorylation, right? Substrate level phosphorylation. That has an efficiency of 50%. This damn mitochondrial oxidative phosphorylation has got only 40% efficiency. Why would evolution choose 40% efficiency with respect, and that too is at the fag end of the cycle. Every molecule of NADH that is synthesized has to go through this system. So why would it choose such an inefficient method? Now, then why is complex 5 NAD base? Most importantly, do you know complex 5, the ATP synthesis enzyme, it doesn't have an ATP synthesis activity in isolation. It has only ATP hydrolysis activity. It doesn't synthesize ATP. So, the moment oxygen you don't have, you see the cells deplete ATP. Now, what is the evolutionary reason for such a thing to happen? Why should cells have an enzyme that eats up ATP? The whole reason is, why do, see, if enzyme do a reaction this way and that way, keep on doing this way and that way, there is no point in having that enzyme. Alright, the enzyme exists, some enzymes do this way and that way, but there are definite reasons for that. If you study enzymology, you would know. I will come to this part later when we study the ATPase. Now, next is the oxygen's commitment, fidelity, marriage to complex 4. No detachment. If you see, oxygen is such a fast moving molecule. It has 10 to the power 3 angstroms per microsecond. Oxygen and its reactive oxygen species, they have this much motility. So we have so many metal centers, 1 electron redox active centers and all that. Oxygen will naturally get reduced. You can't say it's a chemical system, oh, just because it's a biological system. Excuse me, oxygen, you are supposed to be wedded only to complex 4. You cannot make it anywhere else. You can't say that. It's a life system, it is a biochemical system. It will produce, it is known to produce. So, this oxygen is put under a dilemma by this APCR hypothesis. Okay, so how can we explain oxygen messing with anaerobic systems? How can we explain in our reductionist system, we can give electrons into the ETC through so many man-made chemicals. So there is no real specificity at all. The electron transfer mechanism is rather a very different one than what is vouched for by the aesthetic perspectives of order-seeking biological chemists. The third aspect is stoichiometry. Stoichiometry is a reaction. See, I showed you the equation. As per the current hypothesis, The equations are all beautiful. So they saw through 1950 to 1980s, all labs would have different stoichiometries. Whether it is with respect to the amount of phosphate incorporated into ATP with respect to oxygen consumed, or with respect to the proton and phosphate ratio. Very different ratios, and the number were non-integral, difficult to explain. And then the aspect of cyanide. You see, milligram per kg body weight of cyanide kills. But cyanide, the Kd of cyanide with complex 4 is in millimolar ranges, approximately hundreds of micromolar to millimolar ranges. Now it is inhibiting at micromolar ranges. Now if you take milligram level of cyanide at the cellular level, at the complex 4 level, it would be much lesser than micromolar, because all that doesn't go into the system. Okay, even with that calculation, and you should understand the physiological pH is 7.4, where cyanide binds in the anionic form. The pKa of it is 9.4. It doesn't get so, and cyanide is an anionic species. It will not be preferably chosen in the phospholipid environment. Cyanide inhibition is not explained. Neither said. There are certain other explanations. I am not going into detail. This is the best explanation that a biochemist would like. Structure-based explanation. Complex 1. See, complex 1 structure is like this. Here is the flavoenzyme where it's supposed to react with NADH, and then there are lots of iron sulfur species like this, and then this is a transmembrane proton pumping region. First of all, electron transfer occurs through here. Proton pumps are here. How can they be connected? Electron transfer is in microsecond time scale. This is in millisecond time scale. How are they going together? Very difficult to accept. Then the distribution of these puppies. You see, complex 1, complex 2, complex 3, complex 4, complex 5, cytochrome C is 1:2:2:6:6, that kind of a ratio, 6:9, that kind of a ratio. It doesn't abide by the chemistry. The same reaction ratio was seen in the microsomal system, where heme proteins are high, flavoproteins are low. So modularity is not noted. These projections will give more ROS, reactive oxygen species. Well, the current hypothesis doesn't like my ROS. So if this ROS were to be avoided, why are these sticking out? They should not be sticking out. So things like that. So there are some redox centers that are totally supposed to be out of the route. And if you see, the distances are too far and the redox potentials are not in a favorable thermodynamic gradient. Electrons will go from -350 to -250, but it will be totally different here, -250 to -350. It is not the preferred route. So like that, and there are no evidence for proton pumps. So these are the observations. Now I am coming to my data. Simple thing. Chemiosmosis depends on protons. You do a simple Avogadro's number based calculation. Proton is a 1 micron, 0.5 micron diameter cylindrical object. You see, calculate how many protons are in the mitochondria. You get about 10 protons. How many protein complexes in a mitochondria? Mitochondrion? 10,000. Complex 1, complex 3, complex 4. So if there are one of those 15 steps, these are involved. And the overall electron transport chain is supposed to work at 10 to the power 3 per second. How can it work? If I have two slow reactions, it cannot give a hyper-concerted faster reaction. So this can never work. So if you see the coenzyme Q cycle, that is the funniest thing I have ever seen. Okay, at one such step, it has to bind with coenzyme Q reduced, coenzyme Q oxidized, cytochrome C reduced, all that. It has to do at the same time, and it has to bind proton also. You can imagine. So 314 molecules binding at the same time, coenzyme Q receiving electron, giving electron to the same moiety for something to work doesn't make thermodynamic sense at all, kinetic sense, chemical sense. Most importantly, they found that between two redox centers of heme A, see complex 4 has two centers, two heme A's. They tried to find, this is just 6 angstroms, 6 to 7 angstroms. They tried to check the rate of transfers in aerobic condition and anaerobic condition. If it is through Marcus outer sphere model, anaerobic or aerobic model should not make a difference. They found that in the absence of oxygen, the rate was less than or equal to 1 per second. When they pulsed it with oxygen, they found that 1500 per second. 1500 per second is the rough ETC rate. So you can see, oxygen is obligatorily required. Very importantly, Kd is around millimolar range for oxygen. But the Km value is in micromolar ranges. If you know, can Kd be ever greater than Km? You know the Michaelis-Menten equation, right? Km is equal to Kd plus K2 by K1. K1 or K minus 1? Okay, whatever. So the point is, the Kd has to be greater, Km has to be greater than Kd. Here it is completely opposite. I had shown in the murburn, in the cytochrome P450, how this came around. I have shown that. These were all explained in the earlier system. So, till now I have debunked proton pump, ETC I have debunked. This is the third logic. This will take you some time to just see, try to see, follow the logic. Step 1. NADH breaking to give electrons is supposed to be the energy releasing step. So let us give it a negative term, okay? The delta energy. Now then, to separate protons from the electron and pump it across the membrane, it will require energy, right? Let us give it a positive value. Now, as per Mitchell's concept, the protons, when they come back into the matrix, it is energetically favorable. So let us give it a negative value. Okay? Now, by simple conservation of energy, we can write magnitude of Y is equal to this plus this. Then, if you imagine that this machinery is very efficient, in which all the energy released is efficiently used to pump the protons out, then the P and X will be equal, which will mean that Y tends to 0, which in essentiality means that the energy spent for pumping protons out cannot be used to anyway recycle. You put a balloon, fill the air, let it go, it goes. They are two macroscopic systems. They are not connected. Mitchell wanted them to be connected, but they are not. He wanted them to be connected, conveniently connected, for them to have meaning to come back. But for them to stay there only to build a pressure, he wanted them to be disconnected. So even in terms of chemical energetics, if you see, the pumping out basic energy is 40% efficiency. You know, 3 ATP molecules are given by 1 molecule of NADH. If you calculate NADH to oxygen, that redox couple energy equivalent, it comes to 220 kilojoules per mole. So this comes to 48%. how can a 40% efficiency system give 48%? So what John Walker and his co-people have been trying to do is, they were trying to say it is only 2.5 molecules of ATP that are formed. People have been making a hue and cry, it is not 2.5, we get more than 3, we get 3.5, but they are conveniently suppressed. So this doesn't explain the energetics. So even otherwise, if you see the overall glucose metabolism, one molecule of glucose metabolized gives 33 molecules of ATP. If you see overall combustion of glucose, it gives 2937 kilojoules per mole value. So that gives 39%. So ATP formation, overall metabolism, same energy. So what do the other metabolic processes do? They cannot utilize any energy. So clearly this proton pump based mechanism, chemiosmotic process, cannot explain the energetics. Even if we accept that and give it all the benefit and model it, we'll say let there be so many modules, all are perfectly synchronized, and let us use the, Dr. Sikdar has gone, otherwise it would have been nice to have him here. So you can use the Nernst equation to get the value of whatever the potential. The potential required and what Mitchell sought is around 200 millivolts. For that to reach, here is the 90% of the internal protons need to be pumped out. Even if you start with the most ambitious concentration that you want, unreal concentrations, you have 10 inside, 1000 outside, all that, so that the proton pumping efficiency will have to account for every single proton has to go, only then the proton pump will be able to get that potential. So it doesn't work. So with that I have debunked 3 components, and the 4th component I will not go into the kinetics of it. Kinetics is very simple, but simple. Look, if I can, this is something that our Stephen Hawking very beautifully has shown in Brief History of Time. You can take a glass or a teacup, drop it, breaks into smithereens. You can have a reverse video. Now you can play it in reverse, you can imagine it getting formed in reverse. You can take a fruit, put it down in a mixie, you can get, or a grinder or something, you can get pulp and juice at the other end. Try putting juice and pulp from the bottom and get fruit at the other end. It doesn't work. It doesn't work. It doesn't work that way. Why? Because this ATPase has got 10 to the power 7 times more affinity for ATP than it has for ADP. Now, if a transition state is formed, okay, now transition state is formed, it will let go of which one? ATP or ADP? It will let go of only ADP. Why will it let go of ATP? It likes ATP more. Alright? So, what did Paul Boyer say? Paul Boyer first, he wanted to get, sorry about this, I'm very disrespectful here, but he's still living so I can do it. So, first he published, the hypothesis was chemical intermediate. Slater had proposed the first one in 1950s. So, Paul Boyer, first thing he published in Science, phosphohistidine, science paper. Phosphohistidine was proposed to be the intermediate, So, I don't need to respect somebody who just tries to get something somewhere. I like to explain problems. I don't like to put something there and try to say this is right. Right? I like to explore, prioritize, then solve. I just don't like to say this is the cure for everything else. So here, if you see the reverse process, wherein which ADP, PI, all those need to bind, and then the protons will bind at that same time. All these will bind. Kinetics doesn't make sense. I'm not going to talk about the kinetics. The affinity-based argument is more than enough. Affinity-based argument is more than enough. If anybody wants kinetics arguments, I have got it at the end. Now it's already 50 minutes, and now I am going to come to basically the summation of it. Basically, what happened is, have you seen this picture ever? It's a wonderful work by Moritz Cornelius Escher. You see this water, second floor, it falls down. If you see, try to see it here, it is always going down the stream only, downhill. But then again it falls. This is what they achieved with this theory. Honestly, I don't know who gave this theory start. I think it was Leninger. So, though this I can get 2/3, 3/4 of the point defined by a circle. This is nowhere. These are no way defined by circle. Though if I want, I can see it like that. It is not. So there are enough reasons to ask us to move out of the concepts that are advocated till now. Now, why do I say murburn concept is relevant? In terms of the system where I have established it, I have not worked one day on mitochondrial oxidative phosphorylation. I was fired recently, and 6 months I just thought, damn it, I'll fix this thing. So I just had 6 months home, I just did all this sitting at home. Okay, so, but I have seen so many parallels, unbelievable similarities between the microsomal system of the hepatocyte, cytoplasm, and the mitochondrial system. See, the reaction chemistry is very similar. It's believed to be a 2-electron process, and NADPH is here. Here it is NADH, oxygen both sides, like that. The reaction perceived mechanism, distribution of proteins, cytochromes are coming as aids. Reaction center stage is phospholipids. Final products, product is hydroxylated, accompanied by water formation. ADP is phosphorylated, accompanied by water formation. All are multi-enzymatic sequential systems. Similar paradigms. Both are very similar paradigms. So thermodynamic drives were supposed to be the same. All these ideas were changed. All these ideas, all are but similar. Involvement of cyanide, ROS, water formation, all these have already discussed about this. So the new paradigm in which murburn concept works, it works basically in the mitoheterogeneous system. It's a random system. It works. The most important thing is 1-electron reactions are much faster, more efficient, and more energy consuming than 2-electron reactions. And for them, distances, you don't need to have protein complexations and all that. These many species are present. They will easily produce reactive oxygen species. So my hypothesis is like this: oxygen complex 1 and complex 2 gives reactive oxygen species, and then they are modulated by the other complexes. Through this reactive oxygen species, phosphate is attached, and then through that either heat and water can form or ATP and water can form. Very simple hypothesis. It's a very simple chemical reaction. It's a very simple chemical reaction. Okay? Very simple chemical reaction. What are the...
But reactive oxygen species is freely diffusible
Correct.
across membrane.
Yes.
So how it will
Lovely.
drive?
Very good question, Dr. Surya. Very good question. I'll come to that. Give me a few minutes, I'll come to that. Now, if you see the direct evidence why reactive oxygen species are involved, you see the transmembrane potential, the ATP starts getting synthesized here. ROS starts getting formed there. ROS formation is directly correlated to ATP formation. One of the most important evidence that went for the chemiosmotic process was Racker-Stokenius one experiment. What they did is that they took rhodopsin and irradiated with light. Rhodopsin is supposed to pump protons, and what they showed was ATP synthesis. But they didn't realize that rhodopsin membrane is also associated with flavoenzymes, and rhodopsin is always associated with reactive oxygen species, and they had shown in that same system that those very systems also gave random phosphorylation of so many proteins on serine and threonine molecules of proteins. So serine and threonine have, you see, side have hydroxyl groups. Hydroxyl groups are where phosphates are attached. Same chemistry. So it is the same chemistry. And cytochrome P450s, there are many present in the P450s, in the mitochondria. And phosphorylation of xenobiotics is also seen. So that is also another reason. So coming to Dr. Sorolia's valid question. Now what I'm saying is, my hypothesis is, there is a Moore zone. Okay, what is murburn concept? Mild unrestricted redox catalysis. Mild unrestricted or mured burning. Mured is confined burning. That is the reason. Confined burning. The reactive oxygen species are here. Why do we have cytochrome C here? Cytochrome C is here to catch the one electron species that go away. This is the shield of the reactor. I am saying my model is like the earlier one was like a car or like a water dam. My model is like a nuclear reactor or a simple chula. Okay, so what am I saying here? If the reactive oxygen species go that side, they are scavenged by cytochrome C and they come back. If they go this side, they are taken up by SOD and peroxide catalyst. Now, how do I have evidence to that? I'll tell you why. In the xenobatic metabolism, when I put superoxide dismutase in the reaction, nothing happens to the P450 system. But the moment I put horse-radish peroxidase, which has got a transmembrane segment, reaction is completely inhibited. If I take vitamin C and put it inside, nothing happens to the reaction. I put a palmitate chain onto the vitamin C, reaction is completely inhibited. If I take vitamin E, reaction is completely inhibited. If I take Trolox, which is a polar derivative of vitamin E, reaction is not inhibited. So it is the availability at where they work. That's enough. They work beautifully, and all the chemical evidence that we need is already in. All the arguments that we need is already in. But that's a very, very, very important question. See the distribution. This doesn't require modularity. The random distribution, you see the distribution. This is the complex one. This is the reactive oxygen species generator. These are the modulators, these are the stabilizers, these are the scavengers. See how they work on a statistical, stochastic manner. It doesn't need arrangement. It works on a distribution manner. That is the beauty of this system. That is the addressing your question. So now the equations are there. I have put basically it is order and chaos seen in a different way. Order has inherent chaos and chaos has inherent order. ATP and brings in proton. That evolved later to enhance the efficiency of the system. It is not required in the first evolutionary stage. That's what. So basically all roles are reassigned. So I am saying earlier they had put the horse before the cart before the cart, and now I am saying it's the other way around. So all these are completely reassigned. I don't have time, I think I have exhausted my 1 hour. So if my hypothesis is true, I am saying there should be a naturally available nuclear reactor, because the evolution of a mechanism. I searched and I found a naturally occurring nuclear reactor. History has documented 2 billion years ago in Africa, a nuclear reactor was formed, and it functioned for hundreds and thousands of years. So the nuclear reactor model of it's a nuclear reactor model, but the reactive species are not nuclear entities, they are radical species, okay? So that spontaneously evolved and sustained. So my mechanism has a lot of scope for spontaneous evolutionary generation. So it also abides by Occam's razor, one of the biggest yardsticks by which scientific theories and hypotheses should go through. You know how Occam's razor, right? Occam's razor is, if there are 2 or 3 routes in which you can explain, you should take the shortest one. So basically my hypothesis is a tribute to the biomembrane organized structure of mitochondria, distribution of proteins, non-discriminatory, non-special in their membrane, presence of TROS, development of transmembrane potential. My hypothesis explains why you see a transmembrane potential. It is not the generation of a transmembrane potential that gives rise to ATP. It is the generating process of ATP which gives a transmembrane potential. Okay? So how uncouplers work? Because uncouplers have shown they work in my system, work as transmembrane ROS modulators. They don't work as proton pumps. They can modulate reactive oxygen species by protonating the superoxide. So they can explain how the redox potential distribution is. Their stoichiometry can be explained. The structures of complexes. The NADH. Why does it have one proton less? FADH2 has 2 protons, right? NADH has 2 electrons and 1 proton. Why? Why did evolution stick with that? My hypothesis explains. Then role of protons. How does pH gradient form ATP? Incorporation. Oh, this is a wonderful evidence. Mildred Thorne in 1955, she had shown that when ATP was formed, it had multiple. They put oxygen atom. They put radioactive tracer on that. Then they showed that the ATP, one ATP formed that multiple radioactive tracer O atoms. So it is very difficult to imagine that ATP takes ADP and puts different types of, I put one phosphate, then change the phosphate, put another phosphate. That is very highly unlikely. You imagine radical attacking, one phosphate can get exchanged, that oxygen atom can get exchanged multiple times with a solvent very easily. So that can explain Mildred Thorne's very fundamental mechanistic data. Then oxidative stress by low and high oxygen, both leaching of cytochrome C leading to cardiolipin. Why does mitochondria have cardiolipin? Cardiolipin is a negatively charged lipid. It pushes superoxide into the moon zone. That's the reason. And cationic lipids, they are toxic. Why? Because they mess with the raw species at the interface. So you can't have cationic species even if they are good for drug delivery. Why cyanide kills? My explanation can give. The one that is prevailing doesn't give. So mostly, even if my explanation is not accepted, I wish that the current explanation, which is a humbug, is thrown out. Okay, because that is a travesty to human reason. Okay, and most importantly, it addresses several philosophical aspects. Why do we have only a life system giving rise to another life? You need that flame within the mitochondria, the active flame to be passed on by the mother. You can get all the chemicals together, but you can't just put the fire in, right? That comes through that. That's the reason. So many things about life and death, even in a spiritual level. So basically, oxygen, therefore, needed at cellular respiration. It's not at just complex 4. It is the two-phase, Batman's two-phase, it has got good as well as bad attributes. And thank you for your attention. This is the slide that I put always after my talk. I have exceeded my time by about 10 minutes. So thank you so much. Thank you so much. This is my favorite cartoon strip, Calvin and Hobbes. The childlike nature with which we experiment. We might come to false deductions, but then exploration for new explanations, resolving, once again come to prioritizing and searching for pursuit of better reasons is what defines us. So thank you so much. Thank you so much. Thank you so much. That's all. I'm open to questions. I simply believe that this is the most important work in biochemistry for a long, long time. I'm here to beat my own drum. So that